So let's actually do some of the more formal notes. So we're looking at page, no, it's actually page 5. All right, so we're on page 5. All right. So we live in a 3-dimensional world and thus deal with solids or 3-dimensional shapes all the time. And there are literally an infinite number of these shapes. But we'll be looking at the most common ones that will help us model geometric problems. So reading it again. So a prism is a solid that has 2 congruent faces, which are known as the bases. So basically, the congruent faces are the shapes that they're the same size, same shape that make up the top and bottom of whatever 2D figure you're talking about, with all the other faces being parallelograms. 2 examples of right prisms are shown below. So, looking at these 2 right here, why do you think that these are called right prisms? There's right angles in them. So this prism is made up of, what do you think? What's this prism made up of? Rectangles, right? All right. What's this prism made up of? So what's the face of this, or the base? A pentagon. So it's made up of rectangles and a pentagon. So specifically, the rectangles is where the 90-degree angles come from. So what happens is that if you looked at the center of the shape and you drew a line down, these centers or the bases would connect at a 90-degree angle through the center. Same thing here. Centers of the bases, if we cut them straight down from center to center, it would form a 90-degree angle. All right? That's why they're called right prisms. If we cut directly through the center of the bases, it forms a right angle. All right? That's why they're called right prisms. Typically, right prisms have a rectangle or a square or something with a 90-degree angle somewhere in their shape. Yes. Were you not here Friday? Okay. There you go. All right. Now, if we sliced a prism with a horizontal plane, all right, what would the cross section be? So if we cut, it's a little hard to see, but if we cut right here, all right, we cut it using a horizontal plane. So first off, what shape makes up the faces? So what's the basis of this shape made up of? It's a prism. How many sides does that shape have? 6. 6-side shape is called a hexagon. There you go. Come on, guys. Elementary shapes. You got this. All right. So it's a hexagonal prism. So if I cut directly through it, so I go just right through. What shape do I make? I just go cut its head right off. All right. What did I get? If I look at it dead on after I cut through where I drew right here, if I looked at it dead on, what would I get? A hexagon. So it's a hexagon through here. Now, a triangular prism is right here. If I cut it with a vertical plane, all right, so like this. So I went like just right through it, just like that. What happens to it? It becomes a rectangle if you look at it dead on. All right, so typically, depending on the bases of the prisms, typically if you're cutting parallel to the base, it'll become the shape of whatever the base shape is. So if it's a hexagonal prism, it'll become a hexagon. If I cut the one that looks like a pentagon at the top, like just straight through parallel to the base, meaning it doesn't go through the bases, it'd be a pentagon. Whereas if you cut vertically, the shape can vary. More often than not, it's a rectangle. It could be a triangle. Again, it depends on the shape. But typically, if you cut parallel to the bases, it's basically whatever shape the base is. So if it's a circle on the top and bottom, it'll be a circle. If it's a triangle on the top and the bottom, it'll be a triangle. All right. Now, a cylinder is very similar to a prism. All right, except the base face is enclosed by a curve rather than a polygon. So in other words, a cylinder, the only difference between a cylinder and a prism is there's no corners. All right, it's just a can. Typically, this curve is a circle, and the most common is a right circular cylinder. Every can that you will ever see in the supermarket, whether it be soda, green beans, whatever, will be a right cylinder. And it is a right cylinder because if we went from the center of the circle, from center to center of both circles, which they should be the exact same spot, and then you took the radius of one of the circles from center to center, and then one of the radii would form a right angle. That's why it's a right cylinder. So, what are the two measurements that control its size here? I already said one of them. So, think about the formula that we typically use for cylinders. Does anyone remember what the volume of a cylinder formula is? This has height. Height's involved. What's the other one? Not width, but you're on the right track though. If we're dealing with circles, not circumference, we're dealing with circles though, so you're on the right track with circumference. Radius. Now, what two-dimensional shape wraps around the surface of the circle? So in other words, if I had two circles and I was trying to connect them using a different shape of paper, all right, I want them to wrap completely around the circles with no gaps, no breaks. What shape should that paper be? Should it be a triangle, a rectangle, circle? What do you think? It should be a rectangle. So, for example, guys, look at this. If I fold this rectangular sheet of paper around itself, what's that? It's a cylinder, but what's the shape on the bottom? Circle. So, if you used a rectangle and wrapped it around the circles, you get a cylinder. So, the two-dimensional shape that wraps around the surface laterally is a... Oh, no, this one is a... This one's circle. This one is rectangle. Sorry. So when a two-dimensional figure would rotate on one of its sides. So in other words, if you took a sticky note and stuck it to your pencil and you spun it really, really fast, all right, you would start seeing a cylinder because a sticky note's a rectangle and the rotation, which we'll talk about with 7.3 later, makes that cylinder. All right. Now with pyramids. So typically, the ones that we talked about so far, the vertical and horizontal cross sections, or specifically the horizontal cross section, was congruent to its base. But a pyramid is a little bit different. A pyramid is a solid with only one face, and that's what's known as the base. And the polygon of all the other faces are triangles, and they meet at a common vertex, so they meet at a point. So, for example, the left pyramid, what will be the base of this pyramid? Be a what? A square or a rectangle. We can't quite tell. I would call it a square. So, if I cut it horizontally, so right here, the cross section is obviously a square. But does it look like it would be congruent to the base? No. Why would it not be congruent? Well, it's smaller. But think about where we're cutting and what a pyramid looks like. Okay. Yeah, that's a pretty decent reason. So the base is the base. And since we're building a triangle, all right, that means the higher we go up, the smaller our cross section would be. Because if you look at it from the inside of the pyramid, there's less space between the edges of the pyramid the higher you go up or the closer to the vertex that you get. All right. So they would not be congruent to the shapes because of that. I'm not going to really explain why they. So because the closer you get to the vertex, the smaller the cross section. Now, there is a special relationship between them. What do you think it is? So instead of it being congruent to the base, it would be what? So think about math 2. You learned about congruent triangles, but you also learned about what type of triangles? Starts with an S. Not scalene. So we had congruent postulates of side, angle, side, angle, but then you also had blank postulates, which was angle, angle, angle. Nope. Nope. You guys remember similar? Bro, ain't no way. Similar triangles. All right. So they are similar. So that's what they are. So they're not congruent, they're similar. Meaning that they're the same shape, but the size is proportional. Meaning that the size of the smaller cross section is, the sides would be a fraction, an exact fraction of the sides of the base. So same shape, but the size is proportional to each other. It's not the same size. So congruency means same size, same shape. Similarity means same shape, proportional size. Now, Now, under what conditions would the triangular sides of the pyramid all have to be congruent to each other? So, all the triangle sides, so like right here, what would have to be true about the sides of these triangles in order for them to be congruent? What's a postulate that typically proves congruency? So we talked about this in Unit 5. What are some of the triangle congruence postulates? So like blank, blank, blank.
This is a symbol here.
So what does SAS stand for?
Side,
Side, angle, side. That's a congruence postulate. What's another one?
angle,
Angle, side, angle. What's another one? Side, side, side. Now, we don't really know anything about the angles, but what can we conclude about their sides? They have to be equal. All right, so all the sides of the triangle have to be equal to be congruent to each other. So in other words, the base has to be congruent, or the base of the triangle has to be congruent, as well as its what? Height. So if we're looking at a triangle head on, in order for all the sides to be congruent, not just talking about the angles, all right? If we have two congruent triangles, that means the base of the triangle is exactly the same. So these two bases are equal to each other. And the height of the triangle is exactly the same. So the height's equal. That's the conditions. So in other words, the sides of the base have to be equal. And they all obviously have to have the same height. Yes. Yes. All right. Yeah. Yeah. Now, lastly, we got a cone. All right. So when you think cone, you think like maybe an ice cream cone. All right. It's basically similar to a pyramid, except the base is enclosed by a curve instead of a polygon. So, like a cylinder, the curve is most often a circle. So, the most common cone is a right cone, meaning from center to vertex. If we go all the way down and then take the radius of the circle, it's a right angle. All right. Now, if I rotated a two-dimensional shape on one of its sides, what would produce a cone? So, for example, cylinder's on its side. If you looked at it dead on, what 2D shape do you see? A rectangle. So if I rotated the rectangle on its side, it would form this cylinder. But what about a cone? You're looking at it straight on. What shape do you see? A triangle. So if I rotate a triangle on its side, it would form that cone. All right, it'll form the circle that makes up the cone. So instead of a rectangle rotating on its side for a cone, we have a triangle that rotates on its side. So this would be a triangle. And a good way to look at it is that if we have a plane, say we had a triangle right here, and I rotated it all the way around, so I formed a circle. If I drew the 3D shape that it made, what is that? So look at it from a 3D standpoint. What shape would that be? A cone. All right. So that would be a cone. Now, cone cross sections are a bit different. So if I cut completely parallel to the base, what's my cross section? It'll be a circle. Now, if I cut diagonally, think about this carefully. If I cut diagonally, what shape would it form? Not quite a circle. So look more like an oval. If we looked at our GeoGebra for a second, right here. If I looked at the cross section of a cone, all right, I rotated it completely on its side. All right, and looked at the section. It's not quite a circle. It's an oval or an ellipse. So you can either call it an oval or you can call it an ellipse. Either one is correct. Now, this one's a bit weird. If I cut kind of through it, but not quite all the way. So in other words, if I'm looking at it, I cut it like that. So it's kind of diagonal, but not quite all the way through. It would form this shape. Looks kind of like a parabola. Now, you guys probably don't know the name of this shape. It's a very, very, very weird one. And I don't. It's called a hyperbola. All right. So this is called a hyperbola. All right. So it could be we cut diagonally through the base, but it's not center. Now, if I cut completely down the middle and it's perpendicular to the base, meaning that would be a right angle. All right. What shape would it form? A triangle. So this one is when it's parallel to the base. This one is diagonal to the base. This one can be two different things. It can be another diagonal to the base, or it's when you cut vertically but not through the vertex. So basically, if you cut straight down, so if we go back to our GeoGebra, if we cut straight down, but it's not if we cut straight down, but it's not quite through the vertex, it still makes that hyperbola. All right. The only time it becomes a triangle is if it cuts directly through the vertex. So this one is perpendicular to the base through the vertex. Any questions on cross sections and how to figure them out? So the most you got to do with cross sections, guys, is just recognize what they are. All right. You just need to be able to recognize what your cross sections are depending on where you cut, whether that be diagonal to the base, perpendicular to the base, parallel to the base, whatever. So it takes a little bit of critical thinking, a little bit, because you have to be able to take a 3D figure and then think about it in a 2D space. All right. Any questions on cross sections? All right. So hopefully that should help finish up that delta math. That was really short. That was just with straight up identifying. There's also a quizzes for you guys on this. It should already be posted. And I'll go ahead and put the exit ticket up if you want to take care of that too. So there's a delta math. It was only 10 questions. All right. It's basically on identifying cross sections. And then the quizzes